Hello, IB Biology class. This is Miss Sheely with your next installment of your video lecture notes. Today's video lecture notes are covering our ecology unit, and this is Chapter 4, Section 4, Climate Change. This PowerPoint was adapted from Stephen Taylor's 5.2, the greenhouse effect notes that was from the prior curriculum changes. Also, you may notice that we have Morpheus. Say hi, Morpheus, hanging out in the background, being all stealthy. So remember to take lots of notes, write down any questions you have, and then bring those questions to class when we recap our lecture notes. All right, so the first thing we need to know is what greenhouse gases are. And they are gases that absorb something called a longer wave radiation. And they are gases that are trapped in the troposphere, which is the closest level of the atmosphere. It's right below the ozone layer. We have four main greenhouse gases. The first one, well, the four of them are water vapor, carbon dioxide, methane, and nitrous oxide. Water vapor, of course, is formed from the evaporation from the oceans, but also from transpiration of plants. And we get it out of the atmosphere by condensation, which leads to precipitation in the form of rain or snow. Carbon dioxide, as we learned in our 4.3 carbon cycle notes, is released into the atmosphere mainly via cell respiration, but also via combustion of biomass and fossil fuels. And we get it out of the atmosphere through photosynthesis or just dissolving into the ocean. So those are called sinks for carbon dioxide. Methane is the third most significant greenhouse gas. It is emitted from marshes and waterlogged habitats. It is a source of carbon, so we did also talk about it in our carbon cycle notes. But you can also find methane in landfills where organic wastes have been dumped, and we release it during the extraction of fossil fuels or when our polar ice melts. And then the last greenhouse gas that we have is nitrous oxide. Nitrous oxide is released mainly through agriculture or car exhausts, but it can also be released naturally by bacteria. The presence of the greenhouse gases is actually vital to the evolution and the survival of Earth and organisms on Earth. The greenhouse gases in the troposphere, they trap radiation within that troposphere, which raises the temperature. Water vapor continues to retain heat after it condenses. The water absorbs the heat energy and radiates it back to the Earth's surface, but it also reflects heat energy back. So this is why the temperature actually drops much more quickly at night in an area that has a clear sky versus one that has cloud cover. So if you've never noticed that, take notice the next few times you're out. For me, it's really noticeable in the summertime. So without the natural greenhouse effect, which is what we call this, the temperature on Earth would not actually be warm enough to sustain life. There are actually two factors that determine what we call the warming impact of a greenhouse gas. The first is the concentration of the gas in the atmosphere. And this really depends on the rate at which it's released, but also how long on average it stays there. For example, carbon dioxide is going to stay in the atmosphere much longer than water vapor would. Then the next thing, and this is the slightly more complicated part, this is how readily it absorbs long wave radiation. So the Earth absorbs short wave energy and re-emits it as longer wavelengths. And then those longer wave radiations are reabsorbed by the greenhouse gases. And we have a nice visual here. So when you're looking at this visual, you have wavelength in micrometers along the x-axis and spectral intensity along the y-axis. And in your wavelength, we also have the three main categories of light labeled UV, visible, and infrared, with the shorter wavelengths being UV and visible and the longer wavelengths being infrared. So 25 to 30% of the shortwave radiation from the sun, it is actually absorbed before it reaches the Earth's surface, so that doesn't get there at all. Most of this 25 to 30% that's absorbed is ultraviolet light, and ultraviolet light is absorbed by ozone, which is forms a layer. Ozone gases form a layer just above the troposphere. That remaining 70 to 75%, that reaches the Earth's surface, and then the Earth turns it into heat. That heat is then re-emitted by the Earth as long-wave radiation or infrared radiation. 70 to 85% of this long wavelength radiation or infrared radiation is captured by those greenhouse gases and then can be re-emitted back towards the Earth. So it's kind of complicated, but basically the energy just continues. It gets through, it's absorbed, it bounces back up, it's absorbed by gases, and then bounces back down. So it's kind of trapped in this troposphere, kind of going back and forth between the greenhouse gases and the Earth being absorbed and re-emitted back and forth. Interesting to note that without this process of global warming, the average temperature of the surface of the Earth would be up to about 18 degrees Celsius cooler than it is now. Something else to note is that both oxygen and nitrogen are abundant gases in the atmosphere and specifically the troposphere as well. But since they do not absorb long wavelength radiation, they are not considered greenhouse gases. All right, so elevated levels of greenhouse gases, they're strongly correlated with an enhanced greenhouse effect. Does that mean that it is a cause and effect? No, it does not. It just means that there's a strong correlation. As the levels of carbon dioxide, methane, water vapor, and those oxides of nitrogen increase, more radiation is reflected back to Earth instead of being lost in space. And this is called, something else to note is that human-caused climate change is called anthropogenic. And we're going to get into that in just a little bit. This is just kind of just getting into that correlation here. So first we have a table with carbon dioxide temperature over the 20th century, and you can see that the carbon dioxide levels is the green line and the global temperature is in the red line. And you can see that there's a lot of fluctuation in global temperature. And this is, of course, just over the 20th century, so just from 1900s to 2010 about. So when you're looking at this, it does look like there is a correlation, but is this the only greenhouse gas? No. And although we see a correlation, where do we find the evidence for such a relationship? So there's two things I want to show you. One is a little tutorial. All right, so there's no sound for this, but I am going to go through it. I'm not going to read it to you. I'm going to expect that you read it for yourself, but I'm going to pause with enough time for you to read. You can also, of course, note the web address here and go back and do this at your leisure and fast forward through the part right here. All right, and the next thing I want to show you is a talk from the HHMI Howard Hughes Medical Institute. This is from one of their lectures, holiday lecture series.
Let me quickly review for you how this works. So again, the surface of the Earth is heated by the sun. The amount of energy that comes out of the Earth, geothermal energy, is a few thousand times less than what actually comes from the sun. So in certain places it can be important, but overall it's the sun that sets the Earth's surface temperature, not the internal temperature of the Earth. And when the sun shines on the Earth, some of it is actually reflected back to space. Again, more of it if it's on an ice-covered part of the Earth or where there's lots of clouds. And some of it is then absorbed by the Earth. And when it absorbs solar energy in the visible spectrum, what happens is the Earth heats up in response because it's absorbing energy. And when objects heat up, they emit their own radiation, but in a longer wavelength. And so that radiation then heads back towards space. If the Earth had no atmosphere, it would be about 30 degrees colder. So we would actually have a frozen planet. We are habitable because of our atmosphere, and because our atmosphere has some greenhouse gases, in particular carbon dioxide and methane, the most important of which is actually water vapor. Water vapor is interesting. We don't often talk about it as a greenhouse gas, but the reason it's important is it's like an amplifier. It turns over quickly. It lasts in the atmosphere hours to days to weeks. And so as a result, you can think of the other greenhouse gases, carbon dioxide and methane, as the dial, say on your stereo, but it's the water vapor that amplifies the effect because it turns over so quickly. And so what happens is these greenhouse gases, they absorb some of the infrared radiation, the long wave radiation, and re-radiate it both back to space and downward, but they act like a thermal blanket. So they essentially keep the Earth's surface warmer than it would be otherwise. And that's how the greenhouse effect works. And again, this isn't just a theory. We can actually say this is what causes Venus to be 460 degrees Celsius. We know this is, in fact, in the laboratory, we measure carbon dioxide by looking at how it absorbs long wave radiation.
All right, so like I said, that was part of a much longer program called a holiday lecture series, and you can access that. I'll put the link on Blackboard, but I also have a DVD of that talk if you're interested in hearing more. All right, so back to greenhouse gases. So what is the evidence for these increasing levels of carbon dioxide in the atmosphere? Well, recently, and I'm talking in the last 40, 50, 60 years or so, data has been really easy to collect experimentally. In fact, over the last 40-some years, a gentleman named Charles Keeling has measured atmospheric carbon dioxide from his observatory in Mauna Loa, Hawaii. And this information, this data set, which is now known as the Keeling curve, has become an icon of climate science. Almost anywhere you see climate science information represented graphically, especially within the last 50 years or so, you're going to see mostly his data. And his data shows a clear trend, but also shows the annual cycles of rise and fall of temperature. And many field stations use his standardized method. Historical data takes more effort to collect. It's more variable in the reliability of the results that it produces. Mainly what we're using to collect historical data is ice cores. They're a good source of carbon dioxide data because we can analyze the carbon dioxide concentrations of air bubbles that are trapped in the ice. And then we can estimate the year based on the depth of the core. So ice builds up in layers. So the further down the core the ice is, the older it is. You can get over thousands of years in one ice core sample. the temperature of that historical data from the ice core is hypothesized or deduced, it's deduced from the ratios of the hydrogen isotopes that are in the water molecules of the ice cores themselves. So you can see, looking at this graph, that our historical data is much less variable than our current data, and not that we just have more data points, and we're not making deductions with the direct measurement. So it's a little different. All right, so you may see a question where you need to analyze atmospheric carbon dioxide data of a graph. So let's take a few minutes. This is actual data from January 2003 through December 2008 from Keeling's lab at Mauna Observatory in Hawaii. And I just want you to take a few minutes, think about what you see. All right, so what trend do you see, and how would you word a trend? Well, I see that there's an increase in the atmospheric carbon dioxide at Mauna Loa year after year. Every year, it gets a little bit higher. But in my essay, I'm going to want to account for why there is an annual fluctuation. I can draw a line of best fit and show that there is an increase. That's the trend. But now I need to address that there are some fluctuations. So what can I say to address those fluctuations? So take a second to see if you can think of anything that may address those fluctuations. All right, when I'm looking at this data, I notice that there's peaks and valleys forming those fluctuations. And I'm noticing that the annual troughs or valleys in the carbon dioxide data, they correspond with our northern hemisphere summers. If you look, the downward slope begins June, July, JJ. Okay, so if you look at every single one, your peak stops rising and starts falling in that northern hemisphere summer, that June-July period. So why would that matter? So let's continue with that. What does the northern hemisphere have? Well, the northern hemisphere has the greatest land mass at this time of year, and on that great land mass, it has more trees and plants that are leafy or in leaf. Well, what does that have to do with anything? So now I take that to the next level. Well, this increased amount of foliage is going to lead to increased photosynthesis. If I have more photosynthesis, then there's going to be a greater sink or decrease of carbon dioxide from the atmosphere. So now I have just explained why all the valleys are present, but now I need to discuss the peaks. I'm just going to say that the annual peaks correspond with the winters in the northern hemisphere. You could go on to say more explicitly that in the winters of this area, the trees and plants are not in leaf or in bloom, as many of them are deciduous. There's less photosynthesis happening, and so there's a smaller sink from the atmosphere. But that has also already, you would need to look at the point value of the question. If this was a 5-point question, I have very well gotten easily 5 points out of this. All right, so if the concentration of any of the greenhouse gases rises, then more heat will be retained. And if more heat is retained, we should expect an increase in global average temperatures. All right, so what effects could higher global temperatures cause? Well, increased evaporation from the oceans because of increased global average temperature. That's going to make rainfall more frequent, or it could make it more intense when it does come. Higher ocean temperatures, because of the global average temperatures increasing, could cause tropical storms to be more frequent or even more powerful, such as having faster wind speeds. Something that's not frequently spoken about or is overlooked is that changes are unlikely to be evenly spread around the planet. So you could actually have a colder Scotland and Ireland because of changes in the North Atlantic current, bringing in different water temperatures. It's also really important to note that greenhouse gases are not the only factors that influence our global average temperatures. You have something called the Milankovitch cycle, and this is cycles. This is referring to the Earth's orbit and includes things like axial tilt and precession and other aspects of our orbit around the sun. And then also variation in sunspot activity. That's going to influence global average temperature, as well as changes in the reflectivity of our atmosphere. So all of these things go hand in hand, not just greenhouse gases. All right, so I've already referred to or introduced the idea of anthropogenic climate change. This is human-caused global warming, but I want to go into this a little bit more. What we do know, when carbon dioxide concentration goes up, temperature goes up. And when carbon dioxide temperature goes down, temperature goes down. There have been periods of glaciation, when we're looking at our historical data, that both the temperature and the carbon dioxide temperature dropped. During warm interglacial periods, or periods between glaciation, the temperature and carbon dioxide concentration rose. So we've always had a fluctuation. The important thing is that since the Industrial Revolution, the carbon dioxide concentration has risen to a higher point. Pre-Industrial Revolution, our highest point that carbon dioxide concentration rose to during warm periods was between 280 and 300 parts per million. But since the Industrial Revolution, we have hit as high as 400 parts per million. Industrialization is not the only thing. It was not just the Industrial Revolution, but it didn't stop there. Industrialization, deforestation, and pollution have all increased atmospheric concentrations of greenhouse gases. This increase of greenhouse gases to the atmosphere is occurring faster than our plants and oceans can absorb it. So back to that carbon cycle. We don't have a sink that is big enough or fast enough to replenish the amount of carbon that we're putting into the atmosphere. All right, so last thing that I wanted, or one of the last things I want to talk about today is a nature of science, assessing claims and counterclaims. Climate change is a very hotly debated topic. There have been books that have been written about it, both fiction and nonfiction. Michael Crichton has a really great book that talks about scientists, climate science terrorists trying to take over the world and end the world because of climate science data. So, but why is this so? Well, the first thing, scientists innately are trained to be cautious. We're also trained to admit when there are uncertainties. So when we are presenting our data, we're admitting up front that there are uncertainties in our data. Well, why is this a problem? Well, uncertainties can give the impression that the data is weaker than it actually is. And that's something that not everyone understands. Also, global climate patterns are complex, which makes it really difficult to make predictions. If those predictions aren't on mark, some people believe that that is a reason to refute climate change. The consequences of global climate patterns could be severe enough for human and other species that many individuals feel that immediate action must be taken. But there's a lot of people who resist immediate action because they're making money. They're making money burning fossil fuels, or they could have another company or an investment that is also contributing to climate change. So there's a lot of things that you need to take into consideration. You need to be really well versed and look and aware of how to analyze your source. even if it's on the news, just because it's coming from a news source that you believe is credible, don't assume that they've done their fact checking correctly. Make sure that you're looking into the whole article, that you're listening to the whole segment, and even going back and pulling that primary data that they pulled. A lot of times our media just presents things in small clips, and that's not enough information to really get a handle on the data. All right, so that's it for climate change today. I hope that you have enjoyed it, and definitely bring your questions to class so that we can discuss. Thanks so much.